Thank you for joining us. We are the Northwest Midlands IET Committee, and we are hosting the event for tonight. There are a number of things that you can find from the IET that include intelligence and research, journals and books, IET TV, digital library. The link is we're sharing the link, so you can go to that website and find out more. This session of the IET event that we're having tonight contributes towards your CPD, which is continuing professional development. And to find out more about professional development and the IET career, you can go to the iet.org/career. Once again, for those who are joining us, thank you for joining us tonight. You can become a member of the IET if you're not already a member. And the reason why we are IET members, to put it simply, is it's because the IET is where you belong. So why not join us today and become one of the IET members? Once again, for those who have just joined us, thank you for joining us tonight. We'll be starting shortly. Today, we are looking at online engineering. We've got two of our lecturers from Staffordshire University and Harper Adams University. That is Alison Griffiths and Wane. And today they will be talking about how they teach remotely in engineering throughout the pandemic. Right, thank you for joining us. I'll be introducing Wane, who is one of the presenters for tonight.
Hello, thank you very much, Amelia, for that wonderful introduction. And yes, thank you everyone for joining us on this nice evening. And yes, we're going to be sharing some of our experiences of engineering and how on earth do we teach engineering when we can't see people face to face, and how have we coped. But I think we also will be showing what it's like to learn engineering now. Some of you might have done it a long time ago, or some of you might even be not even left school yet. So there'll be a variety of people, and it might be an investigation into some of the tools of today that we use anyway. And we are going to support this with our blog, when we're going to put some of the links in our blog after the event as well. So that would be great for you to share and have a look at that. My colleagues will put the link to the IET Northwest Midlands website. There you can download your CPD certificates, and you can also find the blog as well. So my name is Sam Wane. I'm also the chair of the IET Northwest Midlands area. And it's my pleasure to welcome a colleague of mine who I've worked with for many years, Dr. or Professor maybe, I'm sure she'll correct me, Alison Griffiths, and she's going to start the event. Over to you, Alison.
Hello, everybody. Yes, I'm Dr. Alison Griffiths, and I'm an Associate Professor at Staffordshire University in Electronic and Communication Engineering. So we're going to start the event now. I'm on the wrong screen, but that's a good start. Okay, so this is the layout of what we're going to be doing tonight. So first of all, I'm going to introduce you to Staffordshire University. Some of you may know about us, some of you may not. At Staffordshire, we've been doing a mix of all on campus, blended learning, which is coming in for laboratories. So all students came in for 3 hours at least per week, apart from the fact when we were in lockdown, which was just 3 weeks before Christmas and up until 2 weeks before Easter. I'm going to be introducing some technology enhanced learning tools that we use to encourage engagement in lectures and also tutorials. And also then I'm going to hand over to Sam, who's going to introduce Harper Adams and show the different types of students we have there. He's going to talk about research and give some examples in the Harper Adams laboratory examples. I'm then going to give some Staffordshire University examples. Sam's going to talk about Middlesex University because they've done something innovative that we could all learn from. And then we're going to summarise and conclude. So, engineering at Staffordshire University. So this is our buildings. You may know we're quite close to the railway station in Stoke-on-Trent. We did actually start there, engineering did, before my time. However, it then moved to Stafford on the Beaconside campus where I met Sam. And then we moved back again about 7 years ago, back to Stoke. Now everything's at Stoke. So this is the Beacon building, so with a nod to the Beaconside campus. This is the Mellor building here, and this is the library, and all of engineering offices are in the front here at the library. This is the reception area in the Mellor building. I don't know if some of you have been there. It now doesn't look like that because this area has been converted into the smart zone where we've got 3D printing. We encourage students to come in in their own time and design things and make things. It's very open for students to come in for classes as well as come in in their own time for project work, etc., and clubs. So we're a city centre campus. Here's the railway. These are the buildings that house engineering. Lectures in pre-pandemic could be anywhere, but now we're doing them. Lectures are all online, and they are going to be for next term. Okay, so we were founded in 1914, and in 1934, engineering formed in Stoke. So, for those of you, this is just a quick information about me. I'm the course leader for the several MSc courses: Electrical and Renewable Energy Systems, Electronic and Telecommunication Engineering, and Robotics and Smart Technologies. And I'm the overall postgraduate tour engineering scheme leader. I started my career at GE. It wasn't called GE then. It was called GEC Alstom at the time in Stafford. And I studied part-time. After my 8 years in industry, I've then had quite a lot of time in academia as a lecturer and researcher. and I've just got a bit of information. My interests are wireless communication applications and also electrical applications, but I concentrate on the sensor side and the communication side. So I've kind of gone full circle, really. I'm external examiner because us lecturers don't just stick to our own university. At 2 universities at the moment, Wrexham Glyndŵr and the University of Wales, Trinity St David, and I've previously been external examiner at APU in Malaysia. The other thing that I haven't mentioned is I do lecture a module. We collaborate with certain universities. I collaborate with ECAM in France, which is in Lyon. My first 2 years of teaching those students there, I travelled to Lyon, and the last 2 years I did this remotely. The other thing is we do have quite a lot. In fact, we have more students that are distance learning students than we do face-to-face, which is a combination of part-time and full-time. Those are in the Ministry of Defence. So I've been teaching distance learning since 2010. So that gave me some confidence, apart from worrying about the internet connection, that that we were quite digitally capable when it came to lockdown. Certain things are still more difficult, like not being able to read students' body language to get a feeling of whether they understand you or not. That's why we have to rely on certain tools, because lots of students don't like sharing their video. They don't mind commenting. So this is an overview of the courses at Staffordshire University. We have 7 main themes, so aeronautical, automotive, electrical engineering, which I've already mentioned, electronic and telecommunications, mechanical engineering, and robotics and smart technologies. But we also have a BSc in product design, which is a new course last year. These are all at MSc, MEng and BEng honours and are accredited by the IET. So we have 500 full and part-time on-campus students. Obviously, I've been doing blended learning this year. And we have other partners that provide additional students. And we also have our 600 MOD distance learners that are off campus. Now, those 600 MOD students are a different kettle of fish dealing with our standard students and dealing with our MOD, because they expect to learn in big chunks. So when we provide the information for them, like the lectures, we provide everything up front to them in a package, because they may be traveling, they may be commissioned to do a tour, and they may not have access to the internet, so they want to take everything with them. So there's different things you need to take into account. So a year ago, I did this study. So I sent out a questionnaire in Microsoft Forms to all the students, which there was, at the time, there's 1,350. And it was this time of year, so students were a bit tired. So 8% of the engineering student population answered this survey. And this pie chart over here shows the breakdown of the students that answered. So 20% are the students in France that I've been teaching distance learning because of the pandemic. However, they are normally face-to-face full-time students. 28% were the distance learners at undergraduate. And 34% were standard face-to-face, so they can be part-time or full-time undergraduate students. And then we've got 8% postgraduate students, because the ratio of the students is a lot smaller at postgraduate. It is growing. And then we've got 10%, which are students from different institutions, but they get their award from Staffordshire University, so a partner would deliver it. So approximately 50 respondents have completed the modules completely, fully distance learning. and 50% of them are face-to-face learners. And in semester 2, they had weeks 9 to 13, so just as lockdown hit, they were distance, whereas the rest of the year they were on campus. So in international students, they are the lowest percentage that feel self-motivated for self-directed study, because they assume that they came over to this country to be taught face-to-face. They had the lowest preference of online lectures because they wanted a mix, and the highest percentage preference of real on-campus laboratories, and the highest percentage uses of recorded lectures. Well, everyone was like the recorded lectures because it allowed them to revise. So that's something going to be taken forward. So they got similar views on how the ability to access the internet. Now, this is 90%. However, this was an online survey, so I would expect that they would have internet access because it was online. So that might be slightly skewed. However, I do always allow them to download so they don't have to stream. They find that 53% they think that they can communicate with their tutor or classmates at any time, which is higher than before because of the use of Teams. They believe they have gained problem-solving skills because of COVID, and the confidence in asking questions online is 19%. However, from experience, I believe that the students that are quieter, that don't ask questions when you're face-to-face, they're the ones that ask the questions online. So it's quite an interesting phenomenon. This semester, we have actually done simultaneous teaching, so students could choose to be on campus or online. And I personally found that's really useful because you can see some feedback, but it's difficult because it's like doing this, tapping your head and patting your stomach. But it gives the better of both worlds in the situation that we have. So this is a score out of 5 here. So, and I split them down. I should probably move on, but basically it's these statistics that guided the university to say we're going to go blended learning, because the thing is the lowest score of them all is the labs online. So they prefer the labs on campus. So that's good. This one is about half. A lot of them like recorded lectures, and we've already mentioned problem solving. So I've got a breakdown of the stats here for each category of student. This, by the way, was published by the Engineering Professors Council last August. It was part of a bigger case study. So what I wanted to show you was, this is what a workstation looks like at home. I personally can't cope with a single work screen because I need to see, at the moment we've got lots of people helping. When I'm teaching in class, I need to see the comments and I need to respond straight away. So I don't know if you will have heard of this. If you're a recent graduate, you definitely will. This is a virtual learning environment. 98% of universities have one. What it is you have a separate tab for each module. It's an American system, so it does call it courses. You're only on one course, but in the States they call modules courses. So for every module that you're on, you have a separate link. So all of the content is placed into there, such as lectures, recordings, tutorial questions, lab information, everything goes into Blackboard. You also can submit your coursework. Now, imagine going into this pandemic in the days when I was a student, where you had to actually hand in a hard copy of your assignment. Now, we've been doing this for quite a number of years now, so this didn't bother us for assignments. However, for exams, that was slightly more of an issue because of the IET, or any professional body. we need to have exams, and they need to be in certain conditions. So here we have some links to the videos. So it's a little bit like YouTube, so students can view their videos. The other thing we need to think about is who's engaging in the lecture. So at the moment, because I can't see anybody, I don't know if anybody's listening, I don't know if anybody's gone off and just left the computer running. So you can see here, I've got the names or the initials of students, and I can see how many times they've interacted. Now, this poor student hasn't interacted at all. However, I know that I added him onto my course, and he's my PhD student, so that's why he didn't interact. However, if it wasn't him, I would be able to have an early indication of students not engaging. In lectures, I use hands up, hands down, and comments. The other thing is here we have an example of submission. So we have had students write their exam down and then scan it in. In maths, they use Mobius software. We subscribe to this software, and it randomizes numbers. So every single student would essentially get a separate exam, and it would be automatically marked. So this is an example of Turnitin. So this is a document that I created, and you'll see that it has 94% similarity, which means I've basically gone on the internet and copied a bunch of text from 2 different locations, and it's come up. So this is my trial document, and I can see from there that I've copied 58% from Wikipedia and 35% from Britannica.com. So this avoids student plagiarizing, because we don't want plagiarism, because that doesn't show that a student understands anything. We want to know what they understand and that they can reference correctly. I can also mark here. I don't show it in the video, but I can click these dots and I can mark automatically. And I can also make comments within the document, and the student can see this when we release the marks. So the other thing that you might remember about lectures is sometimes you don't want to ask that question to the whole class to hear. Sometimes you want to hang back at the end of the lecture and have a discussion with the lecturer. This is a little bit more difficult in online circumstances. So what's good practice is what I've done is created a Microsoft form and say some general questions. So do you have any questions regarding that? This was a lab session. Do you have any questions regarding the lab so far? So I can see from straight away from this class of 35 that 28% don't have a problem. So that fills me with confidence that they're happy. These were actually the students in France that I never actually met. And then I've said, if you've not answered that, if there's no question, if you do have a problem, then you can feed that back to me. And then I can then answer that question in the next session. So the other thing is we use a whiteboard and live polling. So this is after a session. Within a session, we use whiteboards. Now these can be just the lecturer explaining some experiment or equations or theory, doing a question, but also it's collaborative. So these can be joined so students can work together. And what I tend to do is in a session, we can have breakout rooms. And to avoid the isolation, I put them into pairs. So, and I'll give them a time. I'll put a timer on my screen and give them a certain amount of time to solve a problem. And then we can go back in and share what everybody's done. So, and this is just showing that whiteboard. I can copy images in, and I can use it to explain things. This is a Matlab screen. I'm sure some of you have used Matlab in the audience, even though I don't know who everybody is. Okay, so I can clarify things, and again, I can record all this as I've done here. So the other thing that's really useful is live polling, because I can start explaining something and the lecturer can spend, I don't know, 10 minutes explaining something. But if the audience already know what you're about to say, then I don't know that, apart from asking questions. So I've switched it on its head. It's called problem-based learning. So this is an Arduino Uno, and I've got a bit more in a session later on. So the point here is I ask the question, what is the value written to the serial monitor when the switch is pressed? So and then I give multiple choice answers. So students will then answer these questions in real time. I've got 46 seconds for the question, and 15 students have answered it. So then I can see the answers, I can share the answers with them, and I can then discuss, and we can discuss why they put a particular answer. For example, this one, I had 2, 9,600, and 0 and 1. The answer is 1, as Sam rightly said earlier on. Well done, Sam. But what I'm saying is it's more directed to what the audience do and don't know, rather than me guessing or the lecturer guessing. So I'm just going to try something. We have a Mentimeter. It's not going to be anything too scary. I would just like you to, if you're willing, either on another tab or on a mobile device, if you go to menti.com and put this code, or if you've got a scanning device, you can use the QR code. And I can, I'm asking you to put three words that remind you, that come into your head when you think of engineering. I'm gonna present that. So they were Sam's, weren't they?
I've got a few coming through. Just like to say for everybody, if your face is in, if our faces is in the way, you can always just wiggle your mouse and go on to hide thumbnail video. That's what I had to do. So just at the top of probably my face, right at the top.
Do you want me to turn my video off?
No, because it'll still be as black. But it's you can actually just hide thumbnail video. That's just for everybody, and then you can just bring it back again. Just because Alison, my own head was in the way actually.
So this is just an idea. So you can, incredible women, mathematics, technology is the biggest one, and creative, interestingly. So the larger the word, the more people are using typing it. So it's a little bit like Who Wants to Be a Millionaire, if you've watched that program. But this is a different one. Okay. So how do I?
They're still coming in. That's great.
Still coming in.
Wow. I think the main thing is people feel more like they're heard. You know, they can say things and then they can contribute.
I think I've got. This is the bit. We did actually use a different software to this one that we don't subscribe, so I'm not sure how to get off this screen now. Is
it my turn to present?
It is your turn.
Okay. I'll just share my screen and then you can work it out.
So I'll keep it. I can keep it on. So I'll stop my share.
Okay. I will just share mine then, I think. Okay. Thank you, Alison. Just let it go into presenter view. Hopefully that's all good. Right, thanks, Alison. So the reason why we're both doing this talk is because we're giving perspectives of engineering from two different points of view in a way, because I work at a university called Harper Adams University. I have worked at Staffordshire University, hence I know Alison, and I'm now at a very small, very green location, which is in the middle of nowhere, as you can see here. So we're, it's actually an agricultural engineering, well, no, it's an agricultural university. So we do courses, for example, animals, veterinary, crop management, things like that. But the reason why I'm there is because they have an engineering school. It's a small university, the whole university has about 2,500 students. And in engineering, I think we have an intake of probably about 80 students per year. We do a lot of research as well. And one of our big areas is research into robotics in agriculture. So we're really spearheading a lot of the, well, we have a project called Hands-Free Hectare and Hands-Free Farm, which is quite a big thing that we have. Okay, so just focusing in on engineering, we have the 3 undergraduate engineering courses, mechanical, automotive, agricultural, and then we have some masters, MEng and MSc, mechatronic engineering, which is where really I come in because my area is robotics, robotic engineering. And something that you'll see in this presentation is that we really pride ourselves in hands-on teaching of engineering. We do the theory, but we like to demonstrate as well, as you can see in some of these pictures. One of our lecture rooms up at the top right has got a huge door, so you can drive a tractor into it, or a nifty lift, for example, and actually students can see it and see the data in real times as well. And the reason why we're telling you all this is not that we're trying to sell the university, but it's just putting you in the picture of the difficulties that we have when the pandemic struck and we weren't allowed to go into the university anymore. We were all told to stay at home and then try and work out how we were going to deliver courses. And I'm sure all of our universities probably throughout the world are all probably nodding their heads and saying, yeah, we all had the same issue. The other thing that we have at our university as well is that all students on our university have a 1-year placement in industry, which is paid. They get a full-time wage for that. That's all students, and that presented its difficulties as well. It still went ahead, and when the pandemic struck and lockdown came in, we had students who were halfway through their placement. But that was interesting, but the placements carried on. So we were told to stay at home, and how on earth did we teach? Well, the management came up with a structure that we would record our lectures and have live tutorials. And the live tutorials, we have maximum of 20 students per session. So we'd have a lecture that the students would watch, hopefully before the tutorial, and then we'd have timetabled them in for a tutorial session where in theory there would be a bit of to-ing and fro-ing. In practice, as Alison said, most of the students turn the cameras off. It's very difficult for us to know if anybody's listening, what they're doing. They could be doing absolutely anything, so we really don't know. So we try and get the feedback, as in Alison's Mentimeter. We try and put things into the chat box. We give them things to do. So I've just put this picture here because this is actually my kitchen. I'm in my kitchen right now, and this is what I can see. That's the left-hand side. I've just got a small Surface machine, which is nice because it comes with a pen and you can take it anywhere. But I basically have lived in my kitchen for about a year now, and I've got a nice view of the garden, a nice view of the washing, and a boat there. Compared that to the right-hand side, a student sent me a picture of his setup, which just blows mine out of the water. He's got about 3 or 4 screens there, shared with, he's got a Surface as well, and he's got a screen sideways. So the students who are probably more computer literate than me have actually, I think they've coped pretty well with this online delivery. I think it's the staff who've struggled sometimes. So what I'm going to do is just give you some examples of how we try and bring hands-on learning to you, because we all know that engineering is hands-on. That's why we started engineering in the first place. So let's have a look at an example of sensor data. One of my colleagues sent me this. So it's something that we have done with our students. There's a bit of info here. Where do we use sensor data? Well, these are just the names of modules: instrumentation and measurement, fundamentals of actuation. These are the ones that we actually teach at Harper Adams, and we've got some research projects at the bottom here as well. So I'm going to attempt to give you a live demonstration. And what we're using is Firefox. So Firefox is a way of accessing your smartphone. Your smartphone has got more sensors in than the shuttle that went to when it first landed on the moon. And it's got much more intelligence and computing power. And everybody's got one of these. So why don't we just use these? So Firefox allows you to get access to all of these sensors as long as you've got them on your phone. GPS as well. Can't see that there, but it is there. magnetometers, accelerometers, barometers, which I didn't even know is in my iPhone, but it is. So this is an experiment that we started to do with our first year students. We tell them to open up Firefox. You can download that. You don't have to do this now, but we will put the links in the chat. And when you download Firefox, you get access to your phone's sensors data. And we got the students to download this. It's completely free. And then walk up and down the stairs. We have to say walk, so we don't, they're not going to run. And then they take the measurements, and you can see that there's a nice graph which has been produced, and it's pressure. So we're looking at barometer data, and even from just walking up and down the stairs, what the students can do is then take that into Excel. Or the spreadsheets are available, and do a calibration and work out how high they've actually climbed in that time. So you can see that the height is inverse to the pressure. So obviously, as you go higher, the pressure gets lower, even just up a small flight of stairs. It's quite incredible that your phone can pick up on that. Car engine. So we also got the students to use an accelerometer. And what you can do is put it on the bonnet of your car, start your car up, and then rev your car and find out how much accelerations and can you actually identify what's going on. Now, I think in industry, this has got a very relevant use because you could have accelerometers measuring acceleration in all sorts of machinery in factories, and they could be monitoring to see if bearings are coming loose or if there's anything untoward. So a bit of pattern recognition could be useful there. But as long as the initial part here, these are first year students, they just want to see that what does acceleration data actually look like. And another one that we did was one of the staff did this actually. Whether we recommend the students do it or not, it's up to them. But have the phone in your car. Don't look at the phone in your car, but drive around a roundabout. Go slow around the roundabout, and then you can see a faster circuit around the roundabout is actually shown there. And then straightening up and exiting the circuit is quite useful as well. And then we brought that into a bit of, why would you use this? Well, GPS is fine for measuring position. So if we want to track things, for example, you could use GPS. But what we can do is we can actually use accelerometer data. And that's what we use in laboratories. And then the students learn about different types of sensors, different resolutions of sensors, calibration, but also how to change acceleration into velocity and then into position. So we're integrating data. So this is where we introduced how to integrate, and you can actually integrate using Excel. You get a skateboard, and you strap your mobile phone onto the skateboard, and then you push it and it starts moving. And you can see that the blue line is linear acceleration. So you first push this skateboard and then it starts accelerating. The orange line is velocity. So you've inferred the velocity from the acceleration. And so you've integrated that acceleration. And then the third line, which is the gray one, which is position. So from the velocity, you've integrated that again, and then you've inferred the position of all of that. Now, I think what I'll do is, just before I go on to the next one, is I'm going to stick my neck out here and try and give you a live demonstration. Now, there's a really good thing that you can do with Firefox. I'm just going to reload that window. Hopefully that's going to work. Let's see if that's going to work. Okay, so the good thing you can do with it, once you've downloaded it on your phone, you can see acceleration data. And this is actually just streamed to a local website as well, which is on my computer network. So as I move the phone, you can see the data, moving it in the X, Y, and Z in real time. So it's very easy to integrate this with your phone, download it onto your own computer, take a screenshot, or even just record it and put it into Excel. Now, you can do this with Matlab as well. And I'm not going to steal your thunder, Alison, because I think you're going to show this as well. But there is actually a Matlab app on your phone, which does open up and allows you to save things onto Matlab Drive. But I'll let Alison talk about that in a moment. So I'm just going to go back onto my slides again and just talk about something else. So if you've gone through an engineering degree, you all know and love control theory, I'm sure, and I actually teach control theory. Now, if you don't know what control theory is, in essence, it's how do you control actuators, and how do you read sensor information to make sure that things are moving to where they should be. For example, an aeroplane rudder. If you want to move it to a certain place, you could move a simple sensor input. It could then move a hydraulic ram, which would move the rudder, which is then senses its own position, compares it where you desire it to be, the demand input, and corrects it. And so that's a control block diagram on the left-hand side. You've got your desired position. You've got a PID controller, if you've done any control, and then you've got your actuator. It could be a motor, linear motor, it could be a heater, anything that can make something happen. And then you've got your actual position, and then you've got a sensor, there's a feedback loop. On the right-hand side, just behind my head, you'll see that there's a graph. So it might remind you, if you've done a step response, you demand a position to go to, let's say, 1.2 degrees, and then the actual is the blue line where it's overshot slightly and settled down. So we like to teach our students how to improve on that, how to stop all this oscillation, etc. So I've developed these this little teaching rig, and you can see a graphic of it down below. And each one of the students can have one on their desk. So you've got a potentiometer on the left, you can put in your desired position, and you've got a motor on the right. You can see the arrow, you've got a front and back view of that. And then you've got your controller in the middle, which can do PID. Now, I thought I'd done really well by creating 10 of these for the students. We can use them in the classroom. And then the pandemic hit. So no longer could the students actually access these. And it was a big problem because my entire assignment was built around the students accessing these. So what did we have to do? So I went into the university and set up the rig. So you can see a camera view of the rig at the bottom left-hand corner. You can see the motor, and it's on top of a power supply there. And that's actually a webcam. That is being broadcast onto the internet. Students get a web link, and then they can log on remotely to the computer. So there's a bit of a diagram at the top that shows you that they've got a webcam and it's just feeding back to them. And the results were a bit mixed, I must admit. The connection was a bit sketchy. It was something that we did throw together quite quickly. Also, the students can't access a potentiometer, so I had to rejig the assignments and put on a virtual potentiometer. It was something that was constantly moving through different values. The students could actually remote log onto the computer, though, and then reprogram the controller, and that was what they were tasked to do. Write some C code to read the demand value, read the actual value, and put in a bit of a control loop as well. And what was interesting, these are actually screen grabs from the students' assignments, and you can see that they've taken the diagrams and they've put sketches on, they've put values on, angles, and they've annotated it. So they really use the what they'd got available. What was interesting, though, is I think most of the students seem to log on late at night. So that seemed to suit them better because this was open 24 hours and throughout the weekend as well. And most students seem to log on to it late at night. It worked. I think we could do better, but it worked for what we had at the time. So this is a image of the lab in the middle. That's the student's computer that you see on the left-hand side. And you can see that we actually had to have fans on these rigs because they would overheat a bit. They were in 24-hour use, so the gears started to break down. We had to have technicians fixing them, and we had to have lights on because all the lights in the lab were movement operated, so we had to put inspection lamps so students could actually see these. And for the students' sake, I did release a video on YouTube of myself walking around the lab, just showing how that was working. And what I'll do is, if I can actually find it, which isn't there, it's a bit difficult to see my tabs, I'm afraid, underneath the Zoom thing. So I think I'll just leave that one for now anyway. I'll just go back to. Okay, now moving on from that, I decided that for the next assignment, it would be better to use pure simulation. Now, most of you might realize that Matlab is also online. If you use Matlab, there's an online version. You don't have to install it on the computer. Matlab or MathWorks actually released Simulink online as well. So that could all be accessed and used through a browser, as long as you're at a university that subscribes to all of this. So I produced a complete simulation of a spray arm on the back of a tractor, with a motor system, and then the students had to devise a control system to see if that was working, so they could see if the control was working in a dynamic way as well. Something that quite a few of our students did struggle with, however, and it's Alison wouldn't have had this problem, but a lot of our students are quite agricultural, so they have farms, and their internet access was pretty sketchy at times. So those students either had to download Matlab and Simulink or leave it until they were close to campus. So there were all things, you know, that we were learning as we were going on. Okay, so that's a note for me to shut up and pass back to Alison.
You didn't have to share your slide. Thank you, Sam. I'm going to leave Matlab for a minute. That's the final thing that I'm going to talk about. So I'm going to start off at the first years that are level 4s, if you didn't know, because we used to call them level 1 first years, but because of the years of qualifications, it's now level 4. So first and second year communications. So this is a simple AM transmitter and AM receiver, because obviously I teach communications. In the university, we have these systems which are called tutor TIMs. Now we can plug in and out. They're on like a DIN rail, and I've started off the video. Okay, I'll carry on with the video. Okay, so these are in the lab, and the students connect these to a scope and also to a spectrum analyzer to see the signals in the frequency domain and time domain. So what I've got here is, first of all, I've just got an adder. So I've got a 100 Hertz carrier signal and a 2 kilohertz signal, and I added them together, and the output was shown on the scope. This is, I can switch in, I've got 2 channels, and I can switch whether it's frequency, so the spectrum analyzer, or I can switch back in the scope. It's going to move across to this part is just adding 2 signals together. This part here is we're doing this bit. So we're multiplying our high frequency message with our low frequency, our high frequency carrier with our low frequency message. And I have amplitude modulated signal, which is also shown on a scope. Now, we bought this software quite a long time ago because before our Ministry of Defence students, because they used to come on campus for a full day of labs, which was very, very tiring for both them and us. And now they don't come onto campus at all. And we found that the grades are really, really much better now because they can work at the same pace as other students. Okay, so I'm going to move on from this system. So all students have access to this, or the actual hardware. So I'm going to move on. This isn't my area, but I am interested in this because it has a Bluetooth part. So this is a level 5 mechanical vibration analysis video, and it was made for we call it technical instruction. So this is instructions for a student to actually physically carry this lab out in the laboratory. However, on the pandemic, then the results, it's not quite the same as doing it yourself, but the results could be made available. However, Sam has given me a suggestion for a website, which he will possibly say in a bit, that this experiment can be done. I'm just going to show this video because it does show. Can you hear that sound? No, okay, so I'll do the talking if you can't hear the sound.
Yeah,
so this is the corridor up to the mechanical lab in mechanical engineering. This is the lab sheet, and the students are told to download it. They are then shown the carts and how they would do it practically. They've basically got 2 carts, a red one and a blue one, and they measure the tension of the spring by adding weights to it. and then they connect them via Bluetooth to the computer. They are told to move the spring, the cart to the left. They've got different weight, they've got certain weights on them, and then they can analyze the vibration in 2 dimensions, which is why it's useful for level 5 students. So this is similar to what Sam did, but this is in a controlled environment, so it's calibrated. And that's the Pasco carts. They do work in 3 dimensions because I've taken them on outreach experiments and we've done design a roller coaster with them. I don't have a video of that. Oh, here again. So this is my Matlab example, which allows us to extract the sensor data from your phone. I've just extracted the accelerometer data here just to show you. You do need, hang on a second, I just need to let my cat out before she pulls the carpet up. Sorry about that.
It's all right. My neighbour was about to mow his lawn. I thought I might have had to do a dash as well. It's real life though, isn't it? And it brings, I mean, when you do it in class, you know, it's, I think it just brings it more realistic. Sorry.
It does.
Yeah.
It's okay, no worries. So this is using the Matlab online. Now, with our students, for communications, we normally need to send a lot of data across to get to count how many errors we can have. So it's very computationally expensive. So I suggest all my students download where they can. And we are looking in the future to how we can host it so that they can do it using a virtual machine, but we're not there yet. This year we got students to download everything. So I'm just going to play this. So this is a file that I got, which this is running with Matlab online. Then I've got my phone here, but it's not live because I'm not brave enough to do it live like Sam. I created a video. By the way, all my videos in my presentation and Sam's, we're going to put a blog together, and all the links that you see, I've got a YouTube channel where this talk is going to be on the YouTube channel. So you can see I'm moving my phone here and it's recording it into Matlab, and I can analyze that to later date. So I don't have to worry about Excel. I try to stay away from Excel where I can. I love Matlab. I think I should have it tattooed across my forehead. I can digress. I was talking about Matlab to Matlab, and it was a conference, and I was asked how I taught myself Matlab. Was it through YouTube? And I said, well, when I taught myself Matlab, YouTube didn't exist, and everybody couldn't believe me. So that's how long I've been using Matlab, and I always use it to learn new things. So we'll move on from Matlab there. The other thing that I teach is embedded systems. So this is a level 5 or a second year interfacing and programming course. So the students have all got electronics background, but they might not have a great programming background. Now, Arduinos, I don't know if you know, some of you may have some, but they were designed with school children in mind and hobbyists, maybe people that can't necessarily program. However, as an engineer, we can optimize that. We can use machine language to program it to make it go basically faster. So all I've got here is the standard Blink program, which says turn pin 13 on and off as fast as you can. I don't have any delay. They're commented out. And this is an online platform called Tinkercad, which I use in conjunction with the real hardware. And I do have the real hardware here. However, I found this was blended, so the students can also try ideas out in Tinkercad and not burn any components. But the point I'm trying to say here is in Tinkercad, even though it isn't real time, it still gives us an idea of frequency. So these are oscilloscopes that I can connect. So it's exactly the same program, they're exactly equivalent. It's just this one is addressing the ports with a hexadecimal number. Now, the advantage of this is I can turn on and off multiple ports at the same time. Whereas if I'm doing it using the standard Arduino library, these functions take a long time to implement, to execute. So the on and off time is 33 kilohertz here in Tinkercad for the Arduino program, as opposed to in C or C++, 0.8 megahertz. And I can actually go even faster than that. And this is port addressing, but I can use machine code and take it up by a factor of 10 again. I haven't gone that far. So, by the way, this link is an open link to anyone. If you've got that link, you can copy it if you've got an account. My students copy my examples. And the other thing is when they do an assignment, I ask them to provide a Tinkercad link to me. They have to do it with hardware normally. If they've got the hardware during the pandemic, great. If they haven't, they can give it to me just on Tinkercad. Now, bearing in mind, I've taught this module not just in this pandemic. I taught it last year to 150 French students, and I'm currently teaching it to them now, who I've never even met. Okay, so this is the Arduino we have here, and this is to speed up the I do teach them how to connect it, and in Tinkercad they do have to connect it. 3 examples that I've got actually don't use breadboard, but we do use breadboard. This is the interface, and I have got these open as well, but I'm just going to play the video because I'm not so brave as Sam. So I've got the two here, and I've got, when I click on each of the Arduinos, I can see the code for, this is Arduino 2 and this is Arduino 1. I can run the simulation, and I can't actually zoom. I can't zoom in on this version like I can when I'm online. That's one thing that I'm used to doing. So okay. So I can see that I can measure. I can change the time interval per division on those, and I can measure the frequency. So that was just the simple example. Here we've got a potentiometer, and I'm using pulse width modulation to change the brightness of an LED. I think I've got a threshold, actually, not this one I haven't. I've got a threshold value, so I'm going to turn the LED on and off, but I'm going to measure the voltage across the LED and the current through the LED, and I can also see the scope. And I'm about to press up here. So I can start the simulation. You'll notice I've got a serial monitor. Now, in reality, this Arduino will be connected to a PC with a USB, or you could also use Bluetooth or Zigbee, and this is what students tend to do for their projects. And then you can view the what's on the serial monitor on a local computer, or if it's Bluetooth or Zigbee, or even Wi-Fi, because you can have lots of different attachments to an Arduino, then that could also go up to the cloud and be viewed at a remote location. This example, by the way, it's the same video, so I can't get rid of my scribbles, is 2 Arduinos talking to each other. This is a writer, so it can be two-way communication here. However, I'm just demonstrating one-way communication. So this is the writer, this is the reader. So this is the Arduino that says X is. So that's this Arduino, and this is saying X is just counting up and down. My assignment for the students is to add a lot of components together. I demonstrate each one separately and get them essentially to put it together like a jigsaw, which is essentially what we do in engineering anyway, is we test each thing separately and then keep adding them to a working system, so that hopefully at the end we've got a working system. And like I say, a lot of the students use this experience for their projects later on. Okay, so we'll leave Arduino for now and move on to Matlab. So this year, our university had the academic MathWorks license, which meant we had free access to all Matlab training and also all the toolboxes. So it was like, oh, what assignments can I ask? I didn't know where to start. But the good thing about this training is I actually asked students to complete this training, or some of these training, not all of them, depending on the module and the level. And they get a PDF certificate, and I ask them to submit that, and I give them marks for completing. But it's not just about marks for completing. It means that they enhance their knowledge, which used to be my job. I still need to give them a pointer in the right direction, but I know that once they've got that certificate, that they can do certain things. And then they can use that in their assignments, which they can take further onto their career and for employability, and also do more things. So this is an example of a wireless waveform generator. Now, previously, I used to teach my students to script these things, which made them excellent at scripting. And I found this thing this time, which again, very useful during the pandemic. So I can choose, I can be a 5G, long-term evolution, so 4G, 3G, or just PSK or QPSK. So I can choose my modulation scheme. I can send an ideal modulation. So this is an ideal signal with no noise. This is showing the spectrum analyzer in terms of frequency here. Obviously, I don't have lots of time. I could talk forever about this. And this is the signal in the time domain. So we've got the in phase and the quadrature components. And I can put set interference in the communications channel that I know. So I can then at the end, I can output that to a script. So previously I would teach students how to write these scripts, and this is all automatic now, which means that we can then go a stage up. It's a bit like, as you would say, when we were younger, people said, oh, I used to do mental arithmetic. You've got it easy now because you've got a calculator. So this is sort of taking it the step up. You still need to know the basics, the fundamentals, but we can take it further. So that's one of the things that I use. And then, so that was great because it meant I had lots of new ideas for new assignments because of the pandemic, and it's doing that again. So my last one is a level 7 module called Smart Grids. And again, we had to rethink the assignment because of the pandemic. So we came up with the idea of it being an individual assignment. So a student chose a place on the earth, and we were gonna have a 1 acre photovoltaic farm. What we want to do is to try and make use of the photovoltaic energy and calculate or predict throughout the day, throughout a period or a time period, a year, how much energy we forecast would be taken from the grid, because we want to keep that a minimum. So we're trying to use prediction. So this student here chose the Arizona, so the desert. So it's a very sunny place. They used a software called PVSYST, which was an evaluation. We do have it at university, but the students can download it for a trial period. So if they did come into university, they could use it there, but they also had the option of doing that. So then we needed to import that data into Matlab. So this is essentially it was a file, comma separated variable, is a file that we input into Matlab. So we bring it straight into Matlab, and we've got all the months with, surprisingly, not surprisingly, this data, actually, I'll be honest, isn't from there. This is my data from the Science Centre. So in fact, in April, we've got the highest amount of sun, and then June is a second, and we can see at the bottom there is January. We have got a few repeated colours there, but we've got access to the data in Matlab. So what we did is we manipulated that data, or we pre-processed that data, or I got the students to. So we plotted it in, so these are 24 hours, once an hour, average for the whole year, and asked the students to calculate a load profile, work out how many houses could be supplied, and then design a neural network. Now, these students had never programmed, they'd never scripted before, because they're on a master's program, and they were electrical engineers, and again, none of them had ever programmed Matlab before. They've used Simulink in other modules, but not programming. So this is the demo of the training of the network. It was a simple, I'm going to say a simple network. It doesn't matter the structure for this, the case of this demo, but they would basically run the system and see the error is at a minimum. So it would choose a certain point back in time, it would repeat, and you can see that the error is getting wider and wider. This is another example. We trained it for different numbers of nodes in the neural network. We were limited by the computing power. If we were at the university, we would have had more computing power and been able to get better results. But what we're essentially doing, as Sam was saying, we're actually trying to find the gradient, so a local minimum or a local maximum. So we're monitoring the gradient here, and we want it to be as low as possible. And as you can see, it's going back up there. So this might be the lowest. So we've got certain checks, and what we've got, we train our neural network, and then we validate it, and then we do test it. I don't have the simulation for the test, but we've got a line here, and we can see that the black circles are closer to the line on training than they are in validation. And we can then have a look at the errors, and we can adjust our system, and then we can have some results. So this was a completely new assignment for this year, and the students did. It was a research led type of assignment. So it was a bit uncomfortable for the students because they didn't know the answer. Because for other modules, if they're shown how to do an example, and they can repeat it. Whereas this one was more sort of research led. So it's quite exciting to see the results. And I think that is me for a bit longer. Yeah. I shall hand over to Sam.
There's our reminder. Yeah. Fantastic. Thanks so far, Alison. I'll just share my screen. And yeah, so we've got some chats coming in, which are quite interesting. And quite a few attendees have actually admitted that they do have Matlab tattoos. So there you go.
Wow, I wouldn't have a tattoo.
We're not going to ask where these tattoos are, but yeah, it's really good, and it's good to see the use of Matlab. I think we all know and use it, and of course ThingSpeak as well is a big one on Matlab, which we've all used as well, but I don't think we've got any demos of that today. But we do actually have the product manager from online teaching of Matlab as one of the attendees here as well, which is great. So check the chat. Okay, I'm going to talk to you about some other systems that we've used. And what we wanted to do is really get the students a bit of a feel for real physical laboratory work. And I'll just show you this, and then I'll give you a demonstration. But as you can, if you can probably have to move the camera image around because it's blocking the results here. In fact, I'm going to just close mine down a bit. But what we did is we did the virtual labs. There's a system called virtlabs.tech. It's really good. Have a look. It's very realistic. And what's really interesting about virtlabs is they use data from real experiments. So you can repeat the same experiment and you'll always get some sort of changes, just like you do in a real life experiment. So they are actually, apparently taken real data and they've randomized it in the computer simulation. So it brings it a bit more to life. But yes, we did a bit of a poll and we were saying, would you like to do more virtual lab accesses, even if you had access to physical resources? And all of the students there, agreed, yeah, 100%. And I think what's going to come out of this pandemic is there's no way that we're going to start teaching engineering online, but I think the resources that we've got and that we've learned will really start to add a real value and colour to our engineering courses. So the videos, the tutorials, the online tools that we've learned from, I think is only going to enhance things and things will get better. And then the question, I would like to do more virtual lab exercises, even if I had access to physical resources. You can see the results are a bit more mixed there. We've got, well, probably more on the disagree side, I would say. So, the virtual labs aren't going to replace the physical labs. The students have spoken. They found it interesting, easy to use. Everyone likes, well, most of us like using computers and giving it a go. But you can't beat going into the real thing. So I'm just going to show you Vert Labs, and what's quite nice about it when you start it off is you see this is just one example, and this is measuring power, I think it is. So I'm just going to start running it, and I don't know if you can hear it, but it sounds quite realistic. There's a windlass which is being turned, and then you can see on a meter, and in fact I can zoom in on that meter and you can see the values as it's going in real life. So you can move things around like that. So you can scroll around this lab and it gives you a bit more of a, I think it's going to drop the bucket in a little while or something like that. So there's all sorts of things. You can change the types of material, etc. Yeah.
Sorry to interject. You might want to play the video again. We can still see the virtual labs presentation.
Oh, okay. So it hasn't come on. Maybe, thank you. Maybe I'm not sharing my screen properly. Well, that's good. You get to do it. Yes, I can see that. I wasn't sharing my desktop, I think. Okay, thanks for that. Okay, so let's try that again. Can you see that now?
Yes.
Ah, brilliant. Okay. Thank you, Amelia. Real life, this is what happens. So what you've got is you've got a blackboard, and the blackboard has got the theory on there, the formulae, and there's lots of different ones of this. You can zoom in. So you can zoom in on the multimeter. You can start it moving. You can pause it. You can change rotation speeds, etc. Run it again, make it faster, see how it changes. So that's just, I mean, there's lots of these Vert Labs that you can choose from, which has all gone blank now, but, well, okay, let's go back to my presentation anyway. Right. Oh, yeah, okay, and something else that we used is teaching robotics. So we wanted to be able to teach robotics for undergraduates, postgraduates, and master's students. And we found this system, which is the VEX system. Hopefully you can see this as a web page with a blank screen. So you can write programs in this, and then you can drive a vehicle, for example. You can say drive forward. You could put in a while. You can put a loop in here as well, and then put a if statement. So you're programming in an environment which is like Scratch. So I don't know if you've used the Scratch environment, but it's quite nice to use. You can also turn it into code as well. But let me just put together a simple program which will then, let's say, drive the vehicle forwards. If the left bumper's pressed, then it turns right for 90 degrees. Okay, so let me just run that. And what I should do is it'll load up the playground. And you can see from above your robot moving around when it loads up. Just give it a minute to load up. There we go. So off it runs. And you can even see the part of the code that's being used. So, you can use this in STEM as well, teaching skills. So you can see that's in action. Not very good. I think it's jammed against the wall. So it's not, it just shows the very basics of how you can learn to program. But you can take this further. So, for example, with the master's students, we might be talking about behavior-based robotics. So with behavior-based robotics, we're taking this a bit further and saying, well, okay, if we have a robot and it's running a simple program, let me just reset this and run this program. Okay, and let's say it's running a program. If the right bumper hits, it turns left slightly, and if the left bumper hits, it turns right slightly. And ideally, it should get its way around a room. But in reality, it might get stuck in a wall like that. However, what you can do with behavior-based robotics is actually make the robot get angry. So now people might think, how can you put emotions into a robot? Now, anger is just a term that we use. And what we say is if the bumper gets struck several times before, let's say, 10 seconds, then it changes a anger variable. Every time it gets struck, actually, it increases the anger variable. So you can see anger is number 6 now. But after time, it calms down. So if it gets itself unstuck, the anger goes back down to 0, as it probably will do now. It's angry of 4, so it's not very angry. It's slightly more angry. But if it reaches a threshold, and I've said threshold is throw your toys out of the pram, which means if it gets an anger value of 6, then do something completely different. Now, this is the ideas that they use in the robot vacuum cleaners to actually get their way around a room, for example, because if it's following a simple algorithm of just left movement or right movement, then it could get stuck quite easily, certainly, underneath tables. So with robotics, you can put in extra things, as I've demonstrated here, that you call a variable, let's say anger, and if it reaches a certain threshold, then it just does something completely different. As long as time passed then, so it got calmer. But that's just showing that you can actually use these very simple ideas to really show more interesting points of robotics and more advanced points of robotics there. So yeah, that's the vr.vex.com, and actually you can get 3D images, as you can see here. There's 3D camera view, and you've got different areas, different playgrounds. You can put obstacles in them and see how the robot behaves around obstacles, and you set different challenges, pick up items under the sea, for example, and things like that. But Vex is actually pieces of hardware, so you can buy the Vex kits as well and make them into realistic things. So you can learn to program it in simulation, and then you can actually use it on Vex. Right, what I thought I'd talk about now is what they've done at Middlesex University. And this came to light because we had Alex Jivanovic gave us a talk for the IET about the robot called Senster. And he gave this talk from home, and he was a floating head. It was very good with a black background, and the images were absolutely fantastic. So I asked Middlesex, what did they do in their engineering department throughout the pandemic, and what was their reaction? So it's interesting how different universities reacted in different ways. And what Middlesex did was that they made a very strong decision that everything would be taught online. And then next thing they said is that they need very clear camera systems and video teaching demonstrations. There was a worldwide shortage, as we know, of most electronic components, of video cameras, etc. And they wanted something that could be used by all members of staff, not just within engineering. So what they did was they came up with a very nice solution. They actually used a Raspberry Pi. And the Raspberry Pi had just released a very high quality camera module, which was available in quantity. They used the standard lenses. They wrote some code to enable the Raspberry Pi to output full screen HD video from the camera onto HDMI, which is available on a GitHub link there as well. And they used a selection of motor mounts as well. Mini scaffold pipe, and the lighting. I think the lighting really does make a difference. That circular lighting does really light up a person's face quite nicely. They've also released video switches to members of staff which can switch over different HDMI ports as well and goes into a simple USB computer. Simply operated, the buttons 1 to 4, and it just allows switching between video inputs to show examples going on in the laboratory, back to the lecturer's head, and then maybe a zoom up of something that's going on the desk in front of them as well. So this is an example of Alex talking about forward kinematics, probably in a robot arm. And what's nice about this is you can see how the image is superimposed next to Alex's head. And then there's nothing else, there's no background like I've got here to put people off seeing the rest of my kitchen or anything. It's just a complete focus on what is the focus of their lecture. So yes, they've got a laptop in front of the person, camera mounted at eye level, camera also looking down at the tabletop, a microscope to show small electronic components, and an iPad running PowerPoint. Black curtain behind the person as well. So yes, I thought that was a very nice response to all of that. Okay, so I'm just going to stop there and back to Alison just to summarize, and then we've got quite a few questions coming in on the Q&A, so we can always have a bit of a chit chat as well and find out what people have to say. So I'll pass you back to Alison just to bring up your summary screen.
Typical lecturer trying to multitask. I'm just sending the email. So those two people, Anthony and Jay Alderson from Mathworks, I've just sent you an email. So if it didn't come through, I've typed it wrong.
You don't waste time, Alison, do you?
I have to do it. I have to do things as and when. Okay, so in summary, what we're trying to think of now is what can we take forward to enhance our teaching for the future. So I have put what Staffs is going to keep post-pandemic. So we are going to keep online lectures, even if they are simultaneous. This year we will be doing online, but in the future we will still be recording. And rather than have the whole lecture as the lecturer is speaking, we're going to be a lot more problem based. So the students will be expected to watch smaller snippets of lecture and then be more research focused within so to use the time with the lecturer more productively, to be like as in Harper Adams, more hands-on. So we know that students do like to rewatch the material, and the students need to be able to access and download videos. So I didn't mention, but I do have a YouTube channel because my students in France didn't have access to the same Microsoft account that Staffordshire University students had access to. So I couldn't even mark them. I couldn't output to Microsoft Stream. So I also created the YouTube. And not all of my videos are on there because I've got lots. But some of all the videos for my classes are all downloadable. I want to investigate virtual machines in the future, and I have used the Raspberry Pi for several things, so I want to include that in my teaching. I also want to output the signals from Matlab to the software-defined radio. And again, connect more hardware for remote connection, although we have learned a lot from Sam with the lighting, because the lights in the university do go off if there's nobody present, and also the interesting about the fans and the temperatures. So we could use something to automatically turn a fan on and off. I'm not sure if that's what you did, Sam. So in summary, we have learned a lot and we're continuing to learn. And that's why I'm in academia and research, because I personally like to learn and I like to enthuse my students to learn, and I think that they get that enthusiasm and feedback of it. So if I hand over to you, Sam.
Okay, I don't think I've got a summary slide actually, Alison, but I think it's very similar to yourself. And
so I've stolen your thunder. I apologise.
Oh no, you're all right. You're all right. I think with all of this, it's really one day at a time. We don't really know what's going to happen in another year's time, so we can't even try. But definitely use the online tools. And I'd like to improve on the remote access. I think someone's comment was about the remote access, so we can always answer those questions as well. So yeah, I think we've got a lot to learn, but we love learning because it's a big engineering task, isn't it? Trying to teach engineering in the pandemic. So yeah, lots of nice hardware has come out. So we're open to questions. I think Richard's been very kindly monitoring the Q&A. And Richard, have you got any questions for me and Alison?
We've had.
Shall I start sharing?
Yeah, we've had 6 questions. I'm just going to the top. Jeffrey Anderson asked, how are you handling similarity scoring for assignments that include programming code where the goal is to program in a similar way?
Yeah, it's a good question.
Right. It is, and I was stung by that when I was stung by that when I first started using Turnitin. I had to go through my whole class and use the filter, and it took me forever, and I didn't make that so filter out the code. So what I do now is I provide a separate link, so I get a similarity for the code and a similarity for the report. I do know of Matlab Grader. That's another thing that I'm considering using, and again using this training. I've used Matlab live programming a lot more, and I'm actually doing the calculations and symbolic math. So I actually solved my whole exams in like one Matlab live file, whereas previously I would do it in Excel and submit the results to the external examiner. Whereas this year, for my external examiner, I just sent the Matlab live script, and he was over the moon because he could see everything and know that it was all right. Although I think I've gone off topic there.
Well, you've got to get that tattoo, Alison. I think from my point of view, for the code, I often get the students, I don't really teach coding, but the students can add code if they like. So I don't really mark the program, but they submit it as an image. They do a screenshot, so then it's not picked up by Turnitin. But there's, you just got to, Turnitin will show you what's plagiarized and what's not, so you can just go through manually and see. Okay. Yeah. Thank you, Richard. Is there another question?
Yes, an anonymous attendee. You said the Mobius randomly generates an exam paper for each student. How do you ensure that one paper is not significantly easier than another one, or do you just have to trust the algorithm of the modular system of use?
Right. Okay. My colleagues in the math department are experts at Mobius. From my understanding, what it is you can set the same question but give different values randomly, or you can set a bank of questions and group them together. So if they're a similar, I don't know, for example, in engineering, we might have a question on a topic, and we could ask it from separate directions. So you're given this value, work out this value, and then the same question is given the other value, work out this value. So you can group them together so they get the same question, similar question, because obviously what we need to do is to cover all the learning objectives. So everybody needs to do X, Y, and Z. Let's get the tattoo.
Great. Well, I'm just going to do that because it's gone right off my head, and ask for about the next question, Richard.
Right. How are you handling, hang on, this is Jeffrey Anderson. How are you handling similarity scoring of assignments that include programming code where the goal is to program in a similar way?
Yeah, I think that was the first question, actually.
Yeah.
Oh, that jumped down. I saw something funny happen on the screen. Ian, with the remote access lab, could all your students access the remote tech just thinking about possible firewall issues in latency issues.
Yeah, good question. It was a problem. The firewall did frighten me a little bit. I had to speak with IT nicely, and they had to allow certain computers to be accessible just for that particular part of software. We also had to use a online calendar where students could also use. Now, I use a piece of software called Calendly, which was great. It's just an online calendar where students could put in their slots. But we also had to trust that they were going to do that at that time, and then they would log out at the right time. So we didn't have the time. If we did have the time, we'd love to do it. But where they actually have a time slot, it allows them in and then shuts them down at that time. But that would probably have to be using a Linux system, and maybe I was thinking in the future we'd have a Linux, Raspberry Pi, dedicated online server system, but we just had to make do with what we had. The delay was a big issue as well, because the students had to actually remote into the university onto a virtual computer at the university. Once they were on that virtual computer, then they had to remote into the laboratory with their code. So they had to remote through 2 computers, and yeah, there was a delay. You could still use Windows, you could still actually use the Arduino environment and program it. It was all there, but yeah, there was a noticeable delay. Definitely.
Well, that is teaching them a certain skill set, and to appreciate the delay as well in terms of communications. That's like, I'd love to do that. Yeah.
Well, I'll draft you in. Thank you, Richard. Is there any others?
Yes, we've got one from Yasef saying, should labs be physical or online? Because sorry, my screen's jumping. Because online labs we can't perform practically.
Yeah,
I think. I think that there's good. Obviously, you can't replace an online lab. However, you can prepare for. You can't replace an actual hands-on lab.
Yeah.
But you can prepare for that lab online. And also, in terms of our Ministry of Defence students, the argument is that they're using equipment. I've had this fed back to me several times. They're using the equipment, say, in the aircraft, in the field, all the time, but they don't necessarily understand what they're doing. They're following instructions, whereas by doing the courses that we offer, they then actually understand what it's telling them. So it depends on the student, and obviously you can't replace online labs.
Physical labs.
Physical.
I think with an online lab as well, you've got a simulation, so it doesn't matter if you break it, you just reset it. So to learn how something works, how do we learn? Well, we try and break it, don't we, really? So you just reset, you just refresh your browser. Also, we've always used a lot of online simulation prior to the real thing. For example, if you're learning ROS, Robot Operating System, rather than having a big expensive robot, you program, it goes wrong, it bashes into the wall or something, or off the table, you can learn ROS by using a simulated robot. Then you really know what you're doing, and then once you've passed a certain level of proficiency, you can move on to a real physical robot. We don't have as many of those, but they're more expensive, but it actually reduces the amount of time it takes you to get onto that physical hardware because you've already gone through the simulation. So I think
it also teaches students gradually that in real life, things are not instantaneous, and things do have switches have bounce, whereas in the simulation they will not. So it sort of gradually introduces it rather than all of a sudden, oh, I've got a problem, what can I do? Or and again, I've had students say to me, oh, I've burnt out so many components, or I've fried my Raspberry Pi, I've fried my Arduino. Whereas if I'd have used, I didn't do Raspberry Pi today, I could have done, if I used a Raspberry Pi emulator to start with. And in terms of education, you can then compare the ideal results with the actual physical results, and how you could perhaps optimize what you're doing. Or can you optimize it? Because we like to optimize, don't we?
Okay, brilliant questions. Are there any more?
Yeah.
I think we've got time for a couple more, I think.
Another anonymous one. How important is a good knowledge of Matlab for success in your course? Could students use Python / R as a substitute?
They can, yes. I don't. It's actually the fundamentals that we're teaching. I don't specifically say, or although this time I did say we needed the certificates. However, it was because those particular students had not got much programming experience at all. And we do teach Python, and I do have students who use R as well. It's just that we had all the help in the Matlab, and it's obviously very versatile.
I think if you learn any programming language, like I started off with BASIC, then I moved on to Pascal, and then Assembler. If you learn any language, you can learn any other language. If you've done a bit of Python, you can easily pick up Matlab. And the reason why I think we use Matlab in most universities, I think, is because it's got so many libraries. You don't have to write all of the code from scratch. It'll do things like multi-dimensional arrays quite easily, and you graph it with a couple of 1 or 2 lines of code. And it really does support engineering with all of the toolboxes.
Also, alternatively, you can change your assignment the next year and say you're not allowed to use that library. You've got to write that bit yourself. Yeah. So it's versatile. And yeah, it's just. I mean, essentially, what we're trying to do is to give the students a knowledge base where they can feel comfortable in trying out different things. And as Sam said, I mean, my background was I started off in BASIC, then I taught then I did C, then I did Java. I taught Java. I was actually 2 weeks ahead of the students, so that's quite scary. When I was a brand new lecturer, but then I also went through the same things that the students went through. But Matlab, I taught myself, and that sort of stayed with me. It's my sort of, if I'm trying to learn a new concept, I know that I can model it in Matlab, and then I can understand it.
It does help, doesn't it? Being able to model something, and also as engineering lecturers, we can't teach students everything they need to know to be a good engineer. What we can do is give them the tools to be able to teach themselves. You know, who knows what jobs will be out there. Imagine trying to tell your careers guidance at school that you wanted to be a YouTuber. You know, when we were at school, didn't exist. What kind of jobs will exist when our students graduate? We can't even imagine, but we can give you the tools that gives you the confidence that you can learn and the ability to learn how to learn, really. But Matlab is just a tool. It's not the end, it's not the be all and end all. It's useful. They're really supportive. But using anything, any language will get you the,
I think
matrix laboratory. It's just
an old term at Staff, like an old buzzword at Staffs, is we teach our students to be lifelong learners. And obviously nobody knows everything. And I, as a lecturer, I'm first to admit, if I don't know something, I'll say, well, let's find out then. And having that confidence to say that. And I've done a lot of outreach work, and the teachers can't quite grasp the fact that you don't know where it's going.
And the only way to be at the cutting edge is sometimes to be learning along with the students. That's the way it is, and otherwise you won't be getting the best deal. Fantastic. Is there time for one more, perhaps, Richard?
Yes. How do you handle online exam scripts?
Oh, well, shall I start off?
You can.
This year we've got timed open book. So you've got a strict time limit, and it is actually open book because the students are at home doing it. Now, we can't really monitor if they're all chatting with each other, except for we could individualize the questions. I can't say much more than that because the exam's about to be written next week. But let's just say that there are ways that you could make a question individual, as in every individual student is slightly different anyway. So you can make it different that way. That's what we've coped with. I'm sure some of my colleagues have had other ideas and different ways of doing it as well. Alison, what do you think?
Well, I've been doing exams for a while, and you make it so that because it's open book, you've got to put more content in. And I've also had it where I didn't do it this time, but I have done it where I have breakout rooms, and I can pop in and out of a breakout room and see a student. And I did insist that they have their cameras on, but not everybody has cameras. For the MOD students, they do tend to have cameras. So that's where I started it, doing my online exams. And everybody now, well, most people have access to a scanner or a mobile phone, and they have the exam appears and then disappears. Obviously, they can download it. We disable all the content whilst the exam is on. So again, they could have downloaded it. But then they have 20 minutes at the end to upload everything. And I'm sure we've got some students in the audience that would say that, agree with me, that that is quite a stressful time. So I stay online and students say, I've submitted my exam, can you check? So then I'll check that they've all submitted. And if they haven't submitted, I advise them to email me, because sometimes the system does get clogged up. It's not as bad as it used to be in the early days, as it Sam. I do remember where we did have really bad lockups and all students are trying to submit at the same time. But then other people have devised. I mean, Staffs Uni did have like special regulations in place. So they were more like assignment type assessments, but I still kept to my time constrained task the same, similar to Sam. But I know colleagues did do, depending on the module, they made it more courseworky. But because of the IET accreditation, you do need a specific ratio, 60-40, so 40%, at least 40% examinations. And people do ask, why do we have this exams? Because in the real world, you'll be able to ask colleagues, you'll be able to look at things. And well, we've sort of answered, well, because you've got to be able to work under pressure, and there is a basis of knowledge that you do need to have.
Okay.
So hopefully that's
so I think we're just pretty much out of time now. We've been going for nearly 2 hours. I've just put a quick link to our blog there, which is our IET Northwest Midlands blog, and we will put the links from these presentations in this blog, myself and Alison, as soon as we can. And if you just go back, you've also got files, and then you can see all, you can download an events list as well, and you can see events which are coming up. There's 2 events coming up, Jon Snow and cholera, and we've also got one on agricultural robotics, which will be next month as well. I think they're both next month, but do check the Northwest Midlands website to have a look.
And you have a YouTube channel.
If you put it in the link, Alison, if you've got a YouTube channel.
I've got a YouTube channel, but I put my YouTube channel in the links. I'm saying the IET Northwest Midlands so the whole lecture will be on there.
It will be, and I've put the link on there as well, so you can just follow that too. And also the link for that YouTube channel is on our Northwest Midlands website. Can we just pass over to, and thank you, Richard, for reading out the questions.
Thank you very much.
Okay.
To Mehul to summarise. Thank you.
Thanks, Sam. Well, it was an interesting topic. Thank you very much, Sam and Alison, for sharing this brilliant and insightful information about online engineering with us. We had a great audience and a fruitful Q&A session as well. I'm sure everyone must have enjoyed it. Thank you very much, Richard, as well, for dealing with the Q&A session. And thank you very much, Emilia, as well, for introducing the speakers and leading the whole event. I just want to say, everyone, just don't forget to obtain your CPD certificates. We have provided the links into the chat box. Thank you, everyone, for joining this wonderful webinar. We are expecting you all to see again in our upcoming events. Till then, bye-bye.
Thank you. Thank you, Mehul. Bye-bye, everyone.
Bye-bye. Bye.
Thank
Bye.
you. Thank you for
Bye.
having me.
Bye.
Bye.
Bye-bye.
Bye.
Bye. Bye.
Bye-bye.
Bye.
Bye, everyone.